Thanks to you, Flavio, and to all of you for this invitation to contribute to this interesting discussion. To begin with, I would like to quote Paul Klee, the Swiss-German painter. Klee once observed, Kunst gibt nicht das Sichtbare wieder, sondern macht sichtbar. Art doesn't reproduce the visible, rather it makes visible. Quantum physics could be characterized in a similar way. One could say quantum physics doesn't describe simply the visible reality, rather it allows us to access the invisible. I would like to illustrate this on the basis of same quantum features. Quantum physics is basically contained in this experiment, the single particle interference. Suppose we have here a laser source emitting particles of light, photons, one photon at a time, one photon after another, and these photons impinge this beam splitter, a half-silvered mirror, and we have two detectors watching the two output ports of this beam splitter. In this situation, we will get that this detector counts 50% of the times, you could say 50% of the photons get here, and 50% of the photons get here. Now we could make a bit more complicated setup by introducing here two full mirrors that guide the light in this way to this detector, and the light coming this path is guided by this mirror to this detector. The situation is actually equivalent to this one, and we will get here 50% of the counts and here 50% of the counts. Now, suppose now that we introduce here a second beam splitter, that is a device like this one, which will be now the distribution of counts here and here. Well, if the light particles, if the photons would behave like little bullets, so that they are traveling a well-defined trajectory, then the photons traveling this path 50% will, in arriving here, be distributed 25% will get here, 25% will get this here, to this detector. And similarly, for the photons traveling this path, 25% will get here, and 25% will get here. So, at the end, we should get again 50% here and 50% here. Is this prediction correct? What shows the experiment? Well, the experiment shows that this prediction, 50% here and 50% here, that we should get if the photons are like little bullets traveling either this path or this path, then this prediction, 50% here, 50% here, is wrong. Actually, if we perform this experiment, we will get 100% here and 0% here. Now we could introduce here a little device so that allows us to enlarge this path so that the light would then go so, and here the other path remains the same. It will, and we could enlarge this path little by little. What would then happen? Then we would get this counting rate will drop from 100% to 0%, and then again arise to 100%. And here, complementarily, this counting rate would rise from 0% to 100%, and then again drop to 0%. So you see that here we get this experiment show that this detector, each detector counts taking account of this path-length difference of the situation in these two paths, and similarly for this one. So you could say, well, then in a way the photon travel both paths. One part of the photon is going this path and another part this path, and so here each part of the photon carries the information about the traveled path. But it is not so, because only one of the detectors clicks at a time. And it is amazing. So you cannot explain this neither assuming that each photon travels a good, well-defined path, but neither assuming that each photon travels both paths. So experiments like this led the founding fathers of quantum mechanics to introduce the idea of the collapse of the wave function. This is a cryptic name. It means nothing other than that at the moment of detection there is an agreement between these two detectors establishing which of them counts. So each detector knows how many times it has to count, but at the moment of detection the decision happens, I count and you don't count, or vice versa. That is so this experiment actually led to the insight that we cannot assign properties before detection. We cannot say this photon is traveling this path and this detector will count, or this photon is traveling this path and this detector will count. We cannot say that. Neither can we say that part of the photon is traveling one path and part of the photon the other path, because then both detectors would count together, and this is not the case. This insight that we cannot assign properties before detection led to the discovery of quantum non-locality. Einstein, as early as 1927 in the Solvay conference in Brussels, objected to this interpretation of the coordination at the moment of detection, arguing that we could set then the two detectors far away from each other, and if they are far away enough, such a coordination would require faster than light communication between these two detectors. Astonishingly, Einstein Experiments with these two detectors far away, this thought experiment by Einstein in 1927, has been first realized 6 years ago, in 2012, as a collaboration of the Center of Quantum Philosophy and the group of quantum technologies of the University of Geneva. The experiment demonstrates coordinations between these two detectors, a coordination that cannot be explained by signals between the two detectors, which are upper bounded by the velocity of light. And this means that this coordination at the moment of detection comes from outside space-time. Many quantum experiments have, meanwhile, confirmed correlations coming from outside space-time. And what is more, I will not enter this in detail, but keep this in mind, what is more, these correlations require free will. If the experimenter has free will and can arrange the setup like he wishes, then the answer of nature shows free will as well. In summary, the visible reality we perceive around us emerges from some invisible author with free will. Another important consequence of single particle interference is that we cannot predict the single event, but only the statistical distributions of counts. The probabilistic the probabilistic interpretation of quantum physics was first proposed by Max Born in a 2-line footnote to a paper published in Zeitschrift für Physik in June 1926. Max Born was awarded with the Nobel Prize in 1954, almost 30 years later, for this interpretation, so for the content of a 2-line footnote. In his remarkable lecture, Nobel Prize lecture, at the occasion of receiving the Nobel Prize, Max Born declared, "The determinism of classical physics turns out to be an illusion created by overrating mathematical logical concepts. It is an idol, not an ideal in scientific research." This claim by Max Born contrasts with Galileo's assertion in his famous Lettera alla Gran Duchessa di Toscana. In this letter, Galileo declared, "Nature is inexorable and immutable. She never transgresses the laws imposed upon her." Such a view has important implications for our understanding of God. In fact, such a view is incompatible with miracles. And this was explicitly acknowledged and formulated by David Hume. Miracles are violations of laws of nature. So, if God is the author of these laws, and these laws are inexorable and immutable, by performing miracles, God is contradicting himself. Quantum physics has brought a radical change in our understanding of science. Actually, there is not such a thing like laws of nature. there is no such a thing like inexorable laws of nature, but only regularities which we can grasp and describe mathematically. So, for instance, when we predict tomorrow at 2 p.m. the sun will be at these coordinates in the sky over Rome or over Zurich, we are expressing our belief that this will happen with a near 1 probability, to the extent that we would not enter a bet with payoff 1 if the sun will dance tomorrow at 2 p.m. and payoff 0 if the sun will follow its usual trajectory. Nonetheless, the probability is not absolutely 1, in the sense that there is a law of nature forbidding that the sun dances tomorrow at 2 p.m. The so-called miracle of the sun in Fatima, Portugal, is a good illustration of this state of affairs. It happened on October 13, 1917. Since May 13, 1917, it is reported, the Virgin Mary was appearing to 3 children on the 13th of each month at Cova da Iria. On September 13th, one of the 3, Lucia dos Santos, said, "The Virgin Mary told her, 'In October I will perform a miracle so that all may believe.' On October 13th, at about 2 p.m., the sun danced before the astonished eyes of a crowd of 70,000 people who had gathered at Cova da Iria to see the predicted miracle. The whirling sun was also seen by people who were not at Cova da Iria but in villages nearby. However, in the rest of the world, nothing extraordinary was reported. In fact, the only evidence we have about this extraordinary event is the reports of many eyewitnesses. Independently of whether or not one trusts these eyewitnesses, this extraordinary event illustrates the new scientific quantum paradigm. Ordinarily, with probability near 1, the sun follows the trajectory described by Kepler and Newton's laws. But these laws don't grasp all phenomena contained in God's mind. Ordinarily, God shapes the world according to mathematical equations, so that we can calculate and predict it, develop technologies, and behave conveniently, rationally. Nonetheless, there is no equation that can fit the whole mind of God. Paraphrasing Paul Klee again, one could state, today quantum physics reveals the reality that is behind visible things. The visible world is merely an isolated case in relation to the universe, and that there are many more other latent realities. Indeed, the greatest miracle in Fatima was not what the 70,000 gathered in Cova da Iria watched. the dance of the sun. The greatest miracle was what the 2 billions outside perceived, the sun following the usual trajectory according to mathematical equations God uses to shape a world where we can move and live and be. The great miracle of the ordinary. The miracle of the sun highlights how great this miracle of the ordinary is. I come to another feature, quantum feature, that is the crucial role of the human observer and the experimenter. Let me come again illustrate this with this miracle of the sun. The fact that these 70,000 people perceive the phenomenon, whereas 2 billion around the earth didn't, this can be considered a demonstration of the crucial role the observer plays in quantum physics. In fact, the physical reality is defined on the basis of observations, and observations require observers. For the science we know and do, the observers are we, human persons. The visible world is like speech. Invisible intelligence are speaking to us. The world is speakable because it is spoken. The famous US physicist, quantum physicist John Wheeler was once asked, "But if the universe only starts with our observations, is then the Big Bang here?" Wheeler answered, "A lovely way to put it is the Big Bang here." I can imagine that we will someday have to answer this question with a yes. Actually, there is no physical reality without free choices on the part of the experimenters. It is also interesting to consider the hypothesis of the multiverse, or parallel worlds, in the light of the miracle of the sun. The multiverse is often used to claim that God is not necessary. Exactly the opposite is true. The miracle of the sun can also be considered sort of experimental demonstration of the hypothesis of parallel worlds. God let 70,000 people live in a parallel world, which was not less real than the rest of the world. At the end of the miracle, the two worlds merged again, and only the ordinary world remains. The parallel worlds are different possible worlds contained in God's mind. And thanks miracles, we can realize how great a miracle is the ordinary course of nature. I come and finish with another important quantum feature, the quantization of space-time, and the result of quantum physics, actually in taking account of the results of general relativity, is that space-time is quantized or discrete, granular. There is no continuum, space-time, underpinning the physical reality. We live, so to speak, in a pixelated world, like in a screen of a notebook. In my view, this is another relevant contribution of quantum physics to promoting a more contemplative dimension of science. Indeed, the fact that space-time is discrete or pixelated means that there is no material link between my neurons today and my neurons yesterday. My personal identity cannot be guaranteed by any material substrate. But neither my consciousness warrants my personal identity. While I am conscious, like now, I am aware of my existence. I can claim I am. Nonetheless, during sleep, I lose this awareness of my existence. And this may explain that I cannot myself warrant my personal identity. So, if I keep to my personal identity, I am led to conclude on the necessity of someone who is uninterruptedly conscious and aware of his own being. Someone who can authentically say, I am. Thank you very much for your attention.